Bismillahirrahmanirrahim. In the last lecture, we had discussed the basics of fracture mechanics, and to describe the severity of a crack, we had derived this equation for stress intensity factor, and this stress intensity factor decides whether a crack, when it is subjected to a far field nominal stress of sigma, whether it extends uncontrollably or nothing happens, it's safe. And that is decided by whether this is less than the critical stress intensity factor or equal to the critical stress intensity factor. Now, we had discussed a little bit about the difference between center crack and an edge crack, but I'm afraid we couldn't finish that part of the discussion, and this is probably one of the most misunderstood points as far as students are concerned, because if you look at this formula, there's A here, and there's a convention of using length 2A for a center crack and length A for an edge crack. Now for an edge crack, it seems all right. It is A, it should be A. But for a center crack, instead of using 2A, we use half of the crack length and put it in the same formula. And it makes a lot of sense for doing that, because if we took it as 2A and used that whole thing, then probably we would have needed to derive two alternate sets of theories, one set of formulas to describe edge cracks, another set to describe center cracks. We don't do that. We just have this one formula, and all we need to do is, when it's a center crack, we just take half of the length, and if it's the edge crack, we take the whole of the length. In this way, maybe it is best to think of cracks as the crack length as the crack length per crack tip, because this has two crack tips. It increases, it has tendency to increase in both directions. It can only increase in one direction. So half of it, you can think of it like this: half the crack length belongs to this edge, half of crack length belongs to this edge. And so for each crack tip which actually progresses, you can take half the crack length. Obviously, if you apply this plate to loading and you apply this plate to equivalent loading, this is more dangerous, obviously. And this is part of the question I asked you last time. I hope you have the answer for that. Why does it have a tendency to increase more than this? And as far as the tables are concerned, if you go look up your tables in your textbook, the beta values for this will be greater than the beta values for this. But as far as generally the questions are concerned, whenever there is a center crack, you must use the same formula but take half of the crack length. So this is an important explanation which probably I didn't give last time. Now let's move on to some application of the theory we derived last time. We'll continue with the tradition of trying to do problems from the back of the book or from outside the book, so that you have plenty of practice examples to do. And this problem, there's the first one. This comes from the back of the book, from the SI edition. It doesn't matter, the numbers don't matter. In the non-SI edition, maybe the numbers are different. It doesn't matter. The principles are what counts. So if you can understand the principles, you can understand you can do all the problems. And obviously, if you have a different version of the book, don't worry, just use those numbers, but the principles remain the same, obviously. Now, to take this problem, this is a edge crack, obviously, and The dimensions are given, the width, the heights, the crack length, thickness. A plate, the dimensions are given, is loaded in tension as shown. Obviously this is mode 1. The plate contains a crack 15.65 millimeter long as shown. This is the crack. The material is steel with a critical stress intensity. This is the material property. Critical stress intensity factor of 490 MPa under root n and the yield strength of 1.16 GPa. It's a very strong steel, obviously. Determine the max possible load that can be applied before the plate A yields and B has uncontrollable crack growth. Now we have to check both the modes of failure. It could yield and then have a brittle failure. Obviously then that won't happen. Or it could have a brittle failure before yielding. So we don't know what it is, so we'll have to calculate both. We'll have to do some calculations and find out which happens first. First of all, let's talk about the yielding. Let's check the yielding first. Now let's call it the load that causes yield to be Py. Now Py is simply Sy, this is the yield strength. If the whole of the cross section yields, for that, because general yielding means the whole cross section will yield. And which cross section are we talking about? Obviously the stresses are highest here, so this will yield first and then this keeps on yielding, and what happens is this whole cross section yields. So the area will be this multiplied by this thickness. Let's plug in the values. Py is equal to Sy given to us. This is 1.1 GPa. 1.1 into, let's convert it into MPa. It's always useful, as far as I'm concerned, to do these things in millimeters and newtons. So the stresses come out to be in MPa. This is the area. We're talking about 150 minus the crack length is multiplied with the thickness. So this comes out to be 1182280 newtons, or in a more convenient form, this is the loading that will cause this whole section to yield. Now what about the second possibility, uncontrollable crack growth? When uncontrollable crack growth happens, let's call this load that causes brittle failure. Let's call it PBF. When does that happen? That happens when K becomes equal to K1C at fracture. Now if this happens before the whole of the section has yielded, then it won't be a ductile failure, it will be a brittle failure. Let's plug in the values. The K in this case is, obviously it's a real world situation, this is not an infinite plate, this is an edge crack, so there will be a value of beta. On the right hand side, obviously we know K1C, this is the material property, we can take it from the statement of the question. Now for this kind of a situation, if you open up figure 526 of your textbook, you'll see it deals with a plate with an edge crack, and it has some parameters. Obviously the size of the plate also matters, so H over B here comes out to be 1, H over B, and A over B comes out to be 15.65 over 150 is equal to 0.104. So from these two, we can read from the chart that beta comes out to be 1.3. Obviously, it's a matter of reading from the chart, so it doesn't make sense if you read 1.2987 or something like that. 1.3 is good enough. Now, this is the value of beta, and let's plug this value here. 1.3 into sigma, this we need to calculate by, we know what pi is, and A, obviously it's 15.65. Here we are using this in meters, and this comes out to, this on the right hand side should be 490, which is given. Now here I used beta. Usually I do the dimensions in millimeters, but here obviously I can do it here too, but on the right hand side I have under root m, so either I convert this also, so it is a long process. So here I'll take newtons and newtons, MPAs, but here under the under root I'll take the millimeter value, because we have to keep the units constant on both sides. And here from this, the sigma comes out to be 1699. Now this, as I have stressed in the last video also, this is the far field stress. This doesn't happen here. We don't, for fracture problem, we don't consider this. Obviously the action happens here, but the whole point of the last lecture was it's very difficult to see what stress here is. So we always talk about the far field stress. So when we talk about far field, I mean, this is a good place away from. This is what we are talking about. This is the stress at the far field. Here the stress is very high, but this far field stress causes something to happen, the crack to grow, when a certain balance is achieved. So when we need to find out the stress P, we need to obviously calculate this sigma is this P over A, and this P for our case is BF, brittle failure, which implies that PBF comes out to be sigma into A. Sigma is 1699.89, and in this case A will be the complete area, 150 multiplied by A is complete. This distinction you must keep in mind. What area to take, which area matters when we're talking about the general yielding, the yielding of the whole section yielding, and which area to consider when we are talking about the brittle failure, because for brittle failure it's always the nominal stress, and from here the force comes out to be 2039,867.9 Newton, which can be again expressed in terms of kilonewton, 2039.867 kilonewtons. Now it's obvious that the smaller of the two, this one will happen. This won't happen, because by the time you have enough force to cause brittle failure, this has already yielded. So it's a good situation, it's a good design, because before yielding you'll know what there'll be some sort of a plastic deformation here, and you'll see that something is going to happen, and then it happens. So it gives you a lot of warning. So this is an example of a good design, so that, because you know that failure is going to happen. Now unfortunately it's not always like this. Let's change some numbers, and this I've done deliberately. I've put in some numbers so that the opposite happens now. Same loading, mode 1, there's a crack length, but the length of the crack and the dimensions, all the numbers I have changed, and you can consider the changes when you do them yourself. Now, when it comes to this sort of a problem, again, obviously we'll go through the same process, but now let's see what happens. First of all, we check the yielding. Again, the same process. Load at yielding, again py. Now similarly, the same process I'm going to repeat. Sy into a. Again, I'm talking about, when we talk about area, we are talking about this area. Plastic deformation, yielding will occur here because here the stresses are the highest. It won't occur anywhere else. Put in the values. This time the thickness is different, and you get the answer. This comes out to be 957.6 kilo. Again, this I've taken this in MPa as it is. I have not converted into Pascal or anything, and here I'm using the millimeters, because MPa and this millimeter, so they cut each other, and the answer comes out to be Newton per millimeter is per square millimeter is MPa. So this is our first part of the answer. So whether this will govern or not, we don't know. Let's see the other. Again, from figure 526 of your textbook, same thing, same situation. Now you have h over b comes out to be 1, and a over b is equal to 16 over 100 is equal to 0.16, and this means that beta comes out to be 1.3, similar to the last time. And for brittle fracture, load at brittle failure K1 is K1C at failure, which means same process again. Beta sigma pi A is equal to K1C. Beta comes out to be 1.3. Pi, sigma is sigma. We need to calculate the sigma. Pi into A is equal to 16 into 10 raised to power minus 3. Again, to convert it into, because on the right hand side we have MPa under root meter, not millimeter. So we convert it here, and K1C is equal to 80. And this means that sigma comes out to be 274.48 MPa. Now we need to find out P, and sigma is equal to P, which implies that P is equal to sigma into A, which is 274.48. Again, this A is this one, and this area will be 100 into 12, and this comes out to be 329376 newtons, or 329.376 kilonewtons. Now this is much smaller than this. Had this been smaller, it would have yielded first, then it would have necked and after some strain hardening would have happened, and then it would have broken after a long time. But because this is smaller, it won't yield, this section won't yield, and it will just break in one instant. And this is the governing load now. So this is an example of not very good design, because there'll be no warning. So because although this is slightly different, but if I talk about the uniaxial tension test, in terms of uniaxial tension test, um, we are familiar with this sort of a curve, because there's no sudden failure there. The component yields, and then it strain hardens, and then there's necking off. Actually, the stress goes even higher, and then it breaks at a certain time. But there's a lot of warning, there's a lot of energy that goes in. Here, what is happening is it broke here, somewhere here. There was not even yielding there. The yielding which occurs in these cases when the crack propagates is a very minor, minute, local kind of yielding, and it doesn't take the whole energy required to yield the whole area first, and then up to a certain level of the depth, and then followed by a strain hardening and all that sort of thing. So this is an example where you won't get any warning. You'll think you are just loading it less than the yield strength of the material. 990 MPa is the yield strength, right? And the sigma here, the nominal sigma, is just 274. It's very much smaller than the yield strength, but it will still break. So this is one of those things which engineers have to keep in mind before designing anything. Let's take a different example now. Maybe we'll end with this. Let's take a pipe. Same thing. If there's a pipe, as long as the loading is in mode 1, then it doesn't matter if it's pipe or what. Let's read the statement, and this is again from the SI edition of your book, but doesn't matter if you have a different book. Don't worry, you just use your numbers, doesn't matter. A cylinder subjected to internal pressure Pi has an outer diameter of 350 millimeters and a 25 millimeter wall thickness. You have the outer dia and you have the wall thickness. For the cylinder material, K1C is equal to 80 MPa under root meters, SY is equal to 1200, this is yield strength, 1200 MPa, and SUT, ultimate tensile strength, 1350 MPa. Obviously, this is just put in just to confuse you. It doesn't because if you prevent yielding from occurring, then there's no point of the material going to ultimate tensile stress levels. So this won't, either it will yield or it will break much before that because of this. So it's just there to confuse you. Don't be confused. If the cylinder contains this radial crack in the longitudinal direction of depth 12.5 millimeters on the outside, determine the pressure that will cause uncontrollable crack. Now what we're talking about is this. Let's do it here. There's a crack here. There's a cylinder, obviously it's all round. There's a pressure inside, and this pressure is this pressure you need to find out, internal pressure. There's no outside pressure, and the diameter wall thickness 25, so the inner will be 250, it will be 300 millimeter. Now there is a crack at the outside, radial crack in the longitudinal direction. This sort of a crack is there. We know that whenever a cylinder is subjected to internal pressure, there are hoop stresses, tangential stresses produced in this direction. So this is, what is this? This is mode 1. This is nothing but mode 1 trying to open up this crack. So whether it will yield or it will open up, we won't consider yielding here, but we'll just consider the brittle failure. So for brittle failure, K1, when does the brittle failure occur? K1 becomes equal to K1C. Now K1C is given to you. K is like always. Now we have a different beta here, but and obviously we need some handbooks to find out what the beta here is, but you don't need to worry about that. We have all sorts of tables which have these kinds of information. So the crack length, which is A, is equal to 12.5 millimeter, obviously, because it's not 2A, it's not a center crack, it's an edge crack, so the whole length will be A. Now R naught outer will be 175 millimeters, and half of this, and T thickness is as given 25 millimeter. Ri comes out to be half of this, 150 millimeter. Now in this case, figure 5.30 is the relevant one. For pipes 530, you can look up your book and you'll find out that that corresponds to this situation. The parameters there are Ri over R outer, and which comes out to be 150 over 175, which is 0.857, which is around 0.9. You don't need to be very accurate here, because in any case from a chart you won't be able to read very accurately. As far as the other parameter is concerned, these are the things which characterize a crack, because there are so many cracks, different lengths, different total material, different length of crack, and so on. So you have to find out the value of beta for your crack, and that comes out to be 175 minus 150, which is 0.5. So from this table 530, beta comes out to be 2.4. Putting in the values, 2.4 into sigma, because we need to find out the pressure. First we need to find out the far field stress, and from the far field stress we'll find out the pressure, just like we did in the last problem. We found the stress first, and then from that stress we found out the force required to create that stress. So just put in the values. And sigma comes out to be 168.2 MPa. Now sigma is there. How to calculate this, the pressure P from sigma? Now it depends whether it's a thin walled pressure vessel or a thick walled pressure. If it's a thin walled pressure vessel, it's very easy. We know the hoop stress formula. Sigma is a PR over T. That's very simple. But thin walled pressure vessel has a limit of dimensions. So let's check. Thin walled. We are going to check if it's we don't know. So let's find out R over T. And well, we don't need to be very accurate here, but just take the mean R. And this comes out to be R over T comes out to be 6.5, which is not thin walled, because R over T needs to be 10 or more for it to be a thin wall. So it's a thick walled pressure vessel. Now what should we do? There's no need to panic. In all your exams, in all your quizzes, you are allowed your textbook, and your textbook has all sorts of formulas in it. So if it's a thick walled pressure vessel, nobody remembers by heart the formulas for thick walled pressure vessels. So there's no shame if you don't. Just look at the index, look at the table of contents. Either approach will, you go to the back of the book or you take the table of contents. You'll be led to a certain place in your textbook which has the formulas for thick wall pressure vessels. Now they are a handful. There's a long formula, because thick wall pressure vessels can also have outer pressures and inner pressures and all sorts of things. So for your case, there's no outer pressure. So you'll also find in your book that there is a formula for thick wall pressure vessels, and the equation happens to be 350, and that formula is for internal pressure only, which is the case for us. So for internal pressure only, the formula comes out to be Ri square P. You can check this out. If I make a mistake here, you can correct it and inform me there's a mistake. Or if it's all right, you still have to check for yourself. Don't believe me. Now, this is the formula. Now, we have this, we have the stress values for which we know that it will run away, the crack will run away. So, and that is the tangential stress. But now, this stress value is again for the nominal stress or the far field stress, not the stress here. At a comparable place, if we reach this point, this is the point where we need to find that stress. This stress here will cause this to extend in this direction here. So if we just it means that we have to take, because there's a value, there's a variable r here. R inner and R outer are all fixed, but this R, this needs to be taken as 162.5, because this total 175 minus 12.5, this is the place where nominal value of stress. For the maybe 10th time, I will repeat, and this is worth repeating. Whenever we talk about fracture mechanics, when we talk about the stress, it is a nominal stress or far field stress. So not what the stress is at the tip of the crack. So you remove yourself from this point at the same equivalent point but without a crack, and you put the value here. If you put the value of 162.5 here, then you rearrange, and then Pi comes out to be 28.13 MPa. This is the pressure that will cause. So the question asked us, determine the pressure that will cause uncontrollable crack growth. This is the pressure which will cause uncontrollable crack growth. In this problem, we didn't check the yield, but we can easily check the yield. If we know the yield strength, we know that. But for yielding to occur, this is the area that will yield, and you can do that. So this brings us to the end of this video, and I'll end this with reminding you that these are just these sessions are important, these are valuable, but you must do all these things yourself, and you must also go through your textbook, because there's so much wealth in the textbook that cannot be covered in a lecture of this sort. We'll have question and answer sessions in the class times next week, so please log into Microsoft Teams for that, and make sure you appear after going through this all this material. Thank you.